Howdy folks, I've had a couple of questions about this. This is number four on the My Math Lab for section 14.3. So this problem is a little bit tedious for a couple of reasons. One, it's going to require a very specific substitution if you want to be able to come up with the even numerically come up with the answer quickly. But most importantly, and I don't think this is clear in the question, you must use technology to solve this. And I don't think I was aware of that when I used this question. So you must use technology for this problem. Let's go ahead and see what it looks like here. So we've got a golfer that wants to hit a golf ball 425 yards away, and he's 50 feet. He's angled at 50 feet above the horizontal, and he's going to hit it at a certain initial velocity of initial speed of 120 feet per second. So this ball is going to make some sort of parabolic arc, and the goal is to have it land in the hole. Well, this vector, this initial velocity vector, is missing a direction, and our goal is to come up with what that theta needs to be here. Okay. So what I'd like to do is let's start from the beginning, and let's just say that in an acceleration function for problems on Earth, we usually say, okay, well, the acceleration in the x direction is 0, and the acceleration in the y direction is negative 32, or whatever g is. We're going to use 32 for this problem. And so if we go ahead and find our velocity function is then going to be the integral of the acceleration function with respect to time. And so if we integrate this component-wise, we will have, I guess we could just put a constant here, let's call it C1, comma, negative 32t plus some other constant C2, where we have to satisfy the initial condition that the velocity when t equals 0 needs to be 120 feet per second. And so for that to happen, we would say that the initial velocity vector would be the magnitude of 120. Well, that is so it would be 120 times the cosine of the angle theta, comma 120 times the sine of the angle theta. So we'll go ahead and plug that into our velocity vector. So here we go. We've got 120 cosine of our theta, comma 120 sine of our theta, minus 32t. So then we can come up with the initial displacement vector, or excuse me, we come up with the displacement vector function. So integrating the velocity function gives us the displacement. And so this would give us 120 cosine of theta, and we'll put parentheses around that, t, comma, then we'd have 120 sine of theta, t, minus 16t squared, and then here, for this time I'm going to go ahead and put our constant vector over here. Or what's our constant vector in this case? Well, our constant vector is, we could think of as our initial displacement, and so that would be the initial horizontal displacement, which if we're going to consider, where this guy's, if we're considering that the origin right there, he has the initial horizontal displacement is 0. I'm sorry, let's put the origin down here. And the initial vertical displacement is 50. So we end up with S of t is equal to 120 cosine theta as our angle times t, comma 120 sine of theta t minus 16t squared plus that initial vertical displacement of 50. I might have said horizontal a minute ago. Okay, so what we want to do is we want to go ahead and find theta so that two things are satisfied. so that first of all, our horizontal displacement, 120 cosine of theta times t, we want that to equal. So let me clarify. We're interested in this point right here, right? And what's that point right there? Well, that's going to be the vector. We can think of that as displacement vector 420 comma 0. And so we want the horizontal displacement to be 420, and we want the vertical displacement and the vertical displacement, which is 120 sine theta t minus 16t squared plus 50, we want that to equal 0. Okay. So perhaps the easiest way to do this, well, I don't know if it's the easiest way, if we're going to use technology, which which we're told we should, or I've told you that we should, perhaps the easiest ways to do this is via substitution. So let's go ahead and solve this for t. So if I do that, I get that t is equal to 420 over 120 cosine theta. And then we're going to substitute that. I guess let's maybe number these. That's 1, that's 2. Sub that into 2, the horizontal requirement, or excuse me, the vertical requirement. So let's see here. This would give me 120 times the sine of theta times time, which is 420 over 120 cosine theta, minus 16 times 420 over 120 cosine of theta squared, plus 50, and we want this to equal 0. Okay. So what I'm going to do now is I'm going to go ahead and plug this into, I'm choosing to do Desmos, but you could use any other solver tool that you want. So I'm going to go ahead, Desmos only accepts y and x, so I'm going to say that the y, which is the height, I want to equal 120 sine of x, and I'm not even going to worry about cleaning this up since we're plugging it into a machine. So I'm going to go ahead and graph this in Desmos and then read off the intercepts. Read off specifically, we want to find the location of the X-Intercept. So let me just pull up Desmos. So folks, here I've gone ahead and plug this into Desmos. It's a pretty long expression here. Let me start over. You can see we got y is equal to, and then I've replaced all the thetas with x's just because that's how Desmos works. It only accepts x's and y's if it's going to graph these correctly. And anyway, so here's our expression here, and you can see we've got a pretty messy graph. I mean, if we were to zoom out on it, you'd maybe see a little bit more about what's going on, but not really. So folks, I went ahead and picked a viewing window that made it a little bit easier to see what's going on. And in fact, we could then zoom in on this part a little bit closer. And I'm going to go ahead and ask Desmos to give me the roots for values between 0 and pi. Well, these two roots right here. And I'm going to ask Desmos what those are. We can see the first one, it says it corresponds to 0.412 radians, and the second one corresponds to 1.04 radians. Here's the rub though, folks. If you pick those numbers out of Desmos, that's actually not accurate enough to get the correct answer from my math lab. So I'm going to zoom in a little bit closer, and you see that we get 4.116, and if we go grab another one, the other root over here, if I zoom in on it, till we get to the we get 1.407. So we said that was from Desmos. We got that was for the x coordinates. X equals 0.4116, and the other one was 1.0407. So I went ahead and converted these into degrees, and when I converted them into degrees, we got that the first one came out to be 23.58 degrees, and when I converted the second one into radian, or from degrees into radians, I got 59.63. Okay. And those are the two answers that will be acceptable for my math lab. So folks, this was an extremely frustrating problem in that if you thought you could do some algebra to solve this system of equations, you can't. I mean, you could, but it would be exceptionally messy, and you're still going to need some pretty gnarly trig identities if you're going to try to find an exact solution to that. So anyway, the intention was that you would go ahead and come up with some sort of equation like this, and then plug that into a solver. And from there, if your solver reads the answers in degrees, great. If not, it will read the answers in radians, and you'll need to convert those into degrees. Please let me know if you have any questions on that. Thank you very much.